Welcome to Hot Chips 22. The morning tutorial, non-volatile memory.
Good morning. Can you hear me? Yes. Great. Welcome to the Non-Volatile Memory Seminar at Hot Chips 2010 at Stanford University, and thanks for showing up bright and early here on a Sunday morning. My name is Aurangzeb Khan. Dan and I have had great pleasure in putting the program together today, and we have a distinguished panel of speakers who will speak to us about various aspects of non-volatile memory. Before we dig into the program, a little bit of housekeeping notes. There is a Wi-Fi available for your use. We hope you'll actually listen to the presenters and not just surf the whole time. But Stanford is the name of the Wi-Fi network, and the username is HotChips2010, all capital letters, one word, and then the password is the same, but lowercase. I've got a couple of slides that I'd like to go through to set the stage for the session this morning, and my goal is to get that done as quickly as we can so that we can get to the main topics. But before we do so, I'd like to invite Dan to come up and lay up the program for us today. Dan.
Thanks, Aurangzeb. Let's see here. I don't know if we're quite on the slides. There we go. Oops, are you guys seeing this? Okay. So first of all, I really want to give Aurangzeb credit for doing the work. I really was the main one who twisted his arm to put the program, the tutorial together, but he's really done almost all the work here. So we've tried to lay this out sort of from the traditional non-volatile memory, if you will, which obviously in and of itself, the flash memory world is seeing radical improvements, and obviously all those improvements are really what's led to sort of all the excitement about non-volatile memory and the option of having non-volatile as opposed to rotating storage. So we have Tony Kim from Samsung here. He's a director of technical marketing, and he's going to show us sort of where Samsung's current flash memory is at and where he sees it going in the future. And then we're going to start talking about some of the alternative non-volatile memories. In particular, I think as Tony will explain, there's certainly some challenges upcoming as we get to smaller and smaller geometries with flash. So many people are working on alternatives. So one of those alternatives, Ed Dollar is going to present from Micron about phase change and other aspects of non-volatile memory. And then we're going to have a slight break. And then Saeed Tahrani is here from Everspin to talk about MRAM, magnetic spin memories. And then Paul Kirsch will be here from Sematech. Again, talking about RRAM and, again, futures of non-volatile. And then we have Jim Handy, kind of a little bit more from the application side in an overview and generally the non-volatile versus other forms of memory. And then finally, to wrap it up, Richard Freitas from IBM is here, also talking about the application of non-volatile memory and the futures of non-volatile memory. So again, I don't want to hold it up, but I think you'll enjoy the presentations, and certainly at the end we'll be asking for feedback to improve the tutorial and Hot Chips overall in coming years. So back to Aurangzeb.
Thank you, Dan. So just a couple of quick slides to set the stage. Our motivation for putting this seminar on today was to recognize the pervasive impact that non-volatile memory is having in digital systems and electronic systems. You know, many of us know not too long ago it used to be used mainly for boot code, maybe some lookup tables, things that you needed to get up and running. Flash has changed that completely and dramatically. It's pervasive, it's an enabling technology, and I think pretty much all of us have some amount of it on our person right now. It's ubiquitous in digital consumer electronics, and The scale of its improvement has been quite breathtaking. We've seen annual cost reductions of 50%. These have slowed down a little bit now to 30%, but that over a decade and continuing is an incredible rate of improvement. SanDisk said recently, for example, that it took them 15 years to ship the first 500 million chips, and then they shipped the next billion in just 3 years, and they expect to ship another billion in 2 years. So you can see that the rate of change is actually not slowing down or getting saturated or petering out in any way. It's growing, and we are finding new uses and new applications for this memory. You'll hear much more about that later on this morning. But consumer devices, mobile devices, of course, have had a high degree of these in use for a while. Solid-state disks is an emerging application. And then, as Rich will talk, there are intriguing applications on how this could fundamentally change the performance, cost, area footprint for electronic systems in the future. With all of that, and I think Tony will talk much more about this, there are some challenges also. The technology has pushed so far forward on the lithography curve that there are challenges with scaling the density much more. There are issues with the amount of charge available to store the data and whether the right performance or the right endurance can be improved further, or in fact, if it will potentially degrade. And there are a number of alternatives the industry is looking at to address these challenges, including tying the architecture, the software, and the controller much more closely together, taking steps to do better wear leveling, potentially doing non-planar integration in a monolithic form. With all of that, and of course with the amount of opportunity available, it's no surprise that there are many strong contenders vying for a piece of this pie. We'll hear from a few of them today. Phase change memory has been under development for quite some time, but made some remarkable steps in just the last year. At ISSCC earlier this year, we saw a 1 gigabit memory presented in 45 nanometers. The technology clearly is scalable, has great performance, very good latency attributes, and the write cycles and the bit alterability are very attractive in some applications. There are, of course, challenges. You know, the heat and temperature aspects of it are an area of work in material science, and of course, the fact that the number of write cycles is still finite. And I say that in contrast, for example, to MRAM. Said will tell us more about MRAM technology. But they've had MRAM in production now for a number of years. The density is dramatically different, much lower than the other technologies, but it has no wear-out mechanism. You can see bit-level reads and writes. And with spin-torque technology, which I know some of the folks in the audience are heading companies working on that also, there's a potential for scaling density dramatically. The challenge there appears to be right now in reducing switching currents and in improving the material science of those bits, and I think we'll hear more about that today. And then beyond that, potentially with yet improved scalability, yet improved performance, but also with challenges in its materials development today, in the amount of current that it requires, are resistive RAM devices. And Paul will tell us the work being done at Sematech in that area and potentially give us a glimpse into when we might see that technology realized in products that we could buy. So that's fairly much a deep dive into the technology and into the various aspects of the technology. Then we thought we'd pull back a little bit and take a view in two different dimensions to round the perspective out for you. The first is, how big are these markets today and how will they grow, and sort of what's in the way of them growing further, both from a business side and also from a technology side. Jim's got a great perspective in this area from his work at Objective Analysis, and so he will lead us through that session. And then finally, to wrap it up and to look at the future with new applications that can grow the use of this technology even beyond what we have already seen, we have Rich Freitas talking about storage class memory and how non-volatile memory can enable dramatic improvements in system cost, performance, and physical area requirements. So with that, I'd like to transition and invite Tony Kim to come up and give us Samsung's perspective and his perspective on flash memory. Tony, please welcome Tony to the... Oops. Right here. Yeah.
Okay, thank you. Good morning, everyone. Thank you for giving me a chance to talk about a little bit about the NAND flash technology. Today, I would like to focus on the NAND flash. Even Samsung, we are working with many different memory solutions, such as phase change memory and other new technology. But today, main topic, and my discussion is mainly for the NAND flash. Okay, so my presentation has 4 main sessions. First one, I'm trying to cover the NAND flash technology, and the next second, flash storage management and storage architecture by application, and future trend and conclusion. My presentation will take about 35 minutes. I'll try to my best to finish, and then maybe 5 minutes I have a Q&A session. If you have any question, please ask me. Okay, the first slide that shows the NAND flash technology history. So as we all know, the development of flash memory technology over the past decade has been one of the driving force behind the tremendous growth in the digital consumer application, such as mobile phone, the MP3 player, and digital camera, etc. So as you can see, the in the NAND flash technology is growing faster and faster. So density has doubled every year since 2004. So when I joined the Samsung, our NAND flash business was relatively small. So at the time, our major the density was 16 megabit. So we use the 0.4 micrometer technology. But now we are talking about the 64 gigabit and 128 gigabit in the next year. So this is a quite huge different now. So as you can see, we have 3 different technology as of today: the SLC, single level cell, multi-level cell, and triple level cell. You can see easily, how we are trying to improve some density and the technology. So but the problem right now, everybody understood there are some breaking points on the NAND flash key technology beyond 2013 because of some technology limitation. So I will cover this slide, this area in the next slide, and so lithography is shrinking. It's now getting slow and slow. And also, in opposite side, we have a certain reliability concern due to some endurance and data retention and ECC, some degradation. So as you can see, the MLC, now we are talking about the 1.5K and 1.1K, and each company has a different endurance spec. And also, even the SLC, we couldn't maintaining 100K program erase cycle. That's the one reason we need to talk about how we're going to overcome that limitation. Okay, so this chart shows some influence on the scaling down of a floating gate. As we all know, by shrinking the NAND flash cell, we have several side effects. First one is we encounter a lot of technical challenges, such as increasing the NAND flash cell interference, and also the coupling ratio is decreasing, and also the less charge loss damage tolerance. Those are the key factors we are encountering due to the NAND flash shrinking. So based on that, the NAND flash industry, they changed the spec from the 2007. As we all know, before 2007, we are talking about endurance cycle and data retention separately. So we can supporting the maximum specification endurance cycle. In addition, we are talking about 10-year data retention. But now we are mix all those two factors and say we can guarantee 10% endurance cycle with a 10 years data retention. And also, if you are consume 100% endurance cycle, we only guarantee the 1 year data retention. That is the current standard in in the industry. So that's the main reason why we changed this kind of standardization. That's one of the issue is NAND flash technology limitation. The second one is we need to understand more about the some usage model in real application. That's the one of the reasons. So as I mentioned, the NAND flash is now getting worse. So how we can overcome that some limitation. But the customer has some expectation, like they would like to keep maintaining the endurance cycle. For example, the 2-bit per cell, the minimum requirement is 3K, and 3-bit MLC is 1K. So how are we gonna overcome keep maintaining this kind of endurance cycle with some given advanced technology? So in order to make this happen, the controller need to involve more and more. So when you look at the controller side, what kinds of issue is been behind the controller side? The first, when you look at the left side, that's the legacy controller. Most of legacy controller, chipset and processor, they have ECC engine. So in the memory vendor, we have a certain ECC recommendation, like 4-bit per 512 bytes or 24-bit per 1K byte, something like that. So the controller guy, they are making their chip by having those kind of ECC recommendation. But now this situation is getting worse and worse. So ECC is one of the factor. So by accommodating the 2-bit per cell and 3-bit per cell, we need to have a more strong ECC engine, okay, such as LDPC, for example. So many companies, they are looking at some different ECC engine, and for making the better reliable system. And also we have a different another area which is called the bit error engine. This is another area we are discussing right now. So the NAND flash, we have three main the reliability key factor. One is ECC, number of bit error, and also data retention and endurance cycle. And so for example, in order to make a more reliable system, the controller need to handle the NAND flash error, and also we need to improve the NAND flash the endurance cycle and data retention. So usually, in general, we are talking about several algorithm we are to improve that issue. The first one is randomizer. Some of everyone use a different terminology, but we are talking about scrambler and the randomizer, and this is one of good example. Another algorithm we can overcome that issue is the read retry, and those kind of the bit error engine is need to involve from the some current NAND flash. Okay. And so from this page, I would like to talk about the some NAND flash how the NAND flash side, how we can some shrink again with the most advanced technology, as you know. And today we are already in the 2x nanometer technology. So everybody has a question: how whether we can make a 1x nanometer or more sub 1x nanometer. Is it possible, or do we have any different way to overcome that some lithography issue, etc. So Samsung, we are trying to find some way to replace the NAND flash, but up to now we don't have any good technology for replacing the NAND flash as on the storage solid storage solution. So that's the reason Samsung, we are focusing on the 3D NAND flash technology. So we believe the 3D NAND is the most likely successor for the planar NAND flash in the coming future. So let me briefly explain about the 3D NAND flash style. So as you can see, that we have, the 3D NAND flash has a lot of advantage. The one of outstanding advantage is a high reliability. and because we can use the current process, and so we don't have any the reliability degradation issue, and the so today scaling, in order in order to make a smaller the NAND flash, we are focusing on the lithography shrinking, but from the 3D NAND flash technology, the most important thing is not by the lithography, but by the etching technology. So this when you look at the most 3D NAND flash detail, the 3D NAND flash is fundamentally fundamental concept of NAND, 3D NAND flash operation is exactly same as a 2D NAND flash. So except for the word line wiring. So the backward compatibility with the existing 2D NAND flash is our top priority for the our first generation. And so, and also we have another issue behind the 3D NAND flash. The one of example, the block size will be larger than current NAND flash, and also the density increasing is not exactly same as current 2D NAND flash. So we are looking at the different scaling and the different capacity by having those kinds of 3D NAND flash. Okay, next let me try to cover the flash storage management. So why the NAND flash needed those kind of management from the software side and the hardware side. So let me focus on the from this page for the software point of view. So the NAND flash, as you will all know, the program and the erase unit is different. We call the program is done by the page size unit, and erase is done by the block size unit. So those discrepancy made a more complicated software algorithm and the software involved. So this is one of good example. If you need to update some new data, and you need to copy to the new valid block, and then you program the new data, and then you can mapping the the mapping to the physical block address after updating. Those kinds of some software algorithm is involved for the NAND flash the programming and the erase operation. So we have everyone knows the FTL, flash transition layer, is the one of key element for the NAND flash management. Those FTL manage the mapping, physical to logical to physical address mapping, and also the bad block management, initial bad block and the runtime bad block. Those kind of management is done by the FTL, and also the well labeling. For the lifetime extension. So today we have two different NAND flash solution. One is a pure NAND, and in that case host side handling the older NAND flash issue, FTL, and the hardware is done, handling by the controller side. And also today a lot of many different type of managed NAND is coming out. So the main reason why the NAND flash management is now become more complicated. So they the end customer, they would like to free from the some NAND flash change to the NAND flash technology. So in that sense, managing the NAND type, the solution is more attractive than the bare NAND flash. So let me briefly touch about the some other area we are working through the some firmware. The one is a garbage collection. As you know, the garbage collection is merge the valid data from the scattered block. So those are the one very important the algorithm. We can improve the performance and the some endurance in the aspect. And so when you talk about the lifetime and so we need to understand the wear acceleration index. The wear and acceleration index It represents, how much FTL accelerated the wear out of NAND flash. So, for example, the way number is high, the NAND flash lifetime is shorter, and way is lower, and the lifetime is longer. So that's the reason, we need to, we can easily estimate, some our lifetime based on the some way number. Okay, and also the wear leveling is also very important because we have many different usage model. One is for example, hot data, cold data, or we have a different some terminology. But some of the area is more frequently updated. So the question is how we can balance those different cell. So every cell is used evenly. That's our target. I mean, with wear leveling algorithm. Okay. From this slide, I would like to talk about the flash storage architecture by application. So this chart to show our forecast for the NAND flash market from 2010 and 2015. As you can see, this year we are expecting around 6.7 billion unit. And in 2015, we are expecting 56 billion unit. So we see quite a huge demand from the market. So majority of the NAND flash market driving is from the mobile phone, such as a smartphone and tablet PC and SSD. And also flash card business is now growing and growing. So Samsung, we are expecting around more than 50% growth rate between 2010 and 2015, and so this is this is our the market outlook. And when you look at the market, there are many different usage model and requirements for the NAND flash. So one of a good example, the storage, flash storage driving the performance. For example, SSD, as I mentioned, SSD is one of driving application to improve the NAND flash performance. So how are we going to improve the performance? This is a way we can overcome. The NAND flash has certain performance limitations. So by having the more channel and more way, we can improve the performance easily. So this is one of the example. Number of chip is more chip improve has a more right IOPS number. That's the one of reason. So I'm talking about the performance improvement way because when you look at the application segment, there are many different usage models as I mentioned, not only for the endurance perspective, but also the performance region. So if you see the some area like memory card and MP3, and this area doesn't require high endurance cycle and very higher performance number. So this area, and another area is more high speed in the memory card and consumer SSD and mobile phone, and this is another area. And the third one is the high end card and server SSD and enterprise class SSD. Those kinds of application require different endurance cycle and the right performance. So if you look, so as I mentioned, the NAND flash, we have 3 different technology right now. So this area, high-end market, we are focusing on the SLC NAND, and in the middle range for like a mobile phone and the memory card. So we are focusing on the MLC and also TLC. So those kinds of fragmentation by application and liability is now mainstream. So the most important thing for NAND flash, we need to make our customer happy. They have a different requirements. So how we can meet this requirement? The one of a good example, even the MLC NAND flash, we have 2 different product line. One is enterprise class NAND flash. Another one is a consumer class NAND flash. So those are the one of a good example. So we need to tell our NAND flash to meet the some different customer requirement. Okay, from now on, let me try to cover the future trend. As I mentioned, we have two different directions. One is a pure NAND, direction. Another one is a managed type of NAND flash. From now on, I'm trying to cover the managed type of NAND flash we call eMMC and the UFS. That's the reason why this is one of good example how we're going to overcome the NAND flash limitation. Since today we got many new demand from the market. The main reason why is if you can see the system environment, data environment, and network environment change dramatically. So, for example, system environment, if you can see, before they have only one task, single task requirement. But now we are talking about multitask, and the web access, and also some multimedia play, and full browsing. Those kinds of new system environment make a different memory usage and memory requirement. And when you look at the data environment, before we are talking about text data only and portal. But now we are talking about multimedia application data and web caching and swapping, and there are many new usage models involved due to the some OS change or some new application and also the network environment is changing dramatically in terms of the speed. The speed is now getting faster and faster. So the question is how we can improve our NAND flash based flash solution, storage solution. So let me explain about this a little bit about that. If you can, this chart to show the architecture for high performance and the low latency. In the left side is two-channel storage solution, and in the middle is the one-channel storage solution. The main difference between those two is two-channel storage has SLC NAND, MLC NAND separately. So those are the current architecture most of system they are using. If the case the code stored in the SLC NAND, like SLC NAND and one NAND, and pure data stored in the MLC based storage device such as eMMC. So in that case, the performance, lower performance on the MLC side is not an issue because everything is the more high performance require code and data is done by the SLC part. So everything is okay. But everybody now we are talking about the single unified memory architecture. So in the middle side, so which means that they're trying to merge SLC MLC usage into the one storage device. So that if the case, we have a certain performance issue, and so today I would like to talk about how we can improve this performance issue. And one of our ideas is we can add DRAM in addition, and then we can improve the performance. The performance, when you talk about the performance, there are many the performance we have like a sequential and the random and the sustained performance and etc. So the most important thing is we need to keep maintaining a certain performance no matter what kinds of issue involved. Like worst scenario is now become more important. So let me explain. And so this chart to show some key new feature on the eMMC and UFS. So one of good example is a trim command. Trim command improving the write speed, and also reliable write, HPC, high, interrupt, priority interrupt, and command queuing and sleep power. Those kinds of new features now discussing and already supporting in the eMMC and UFS spec. That's the main reason the environment is changing dramatically. So now we are trying to improve the performance issue and the reliability issue, not only for the NAND flash level, but also the some managed type of NAND flash level. I mean the controller and firmware side. Okay. So this is one of good example. When in order to understand the requirement as I mentioned, SLC, MLC, we need to understand the what kinds of data attribute is involved in the mobile system. The one of good example, if you divide it two, one is a system data, code data, swap data, and another one is the user data. So some of the data is require high sequential performance, sequential read performance. Some of code require the higher random requirement, speed requirement, and the write performance the same. And also the reliability is important, it's not important. So based on this kind of data attribute, we need to divide. We need to decide which kinds of memory we're going to use efficiently. So the MMC already defined those kind of a multi-partitioning method to make this the customer support. So one is a boot area partitioning, and some general purpose partitioning and user data area. So they specify those kinds of area for each code. So this is an example. Boot codes need to be resigned in the some SLC region and user data in the MLC region. So those kinds of data usage model partitioning is now become more important. Okay, and also the trim command is one of the very key feature to improve the performance. So in the NAND flash, we have a certain performance limitation while the merge operation. So merge operation means when you, in order to program, we need to have some free block. But if we don't have free block, we need to erase and then program again. So those kinds of the merge operation involved, the performance is degraded dramatically. So that's the reason the trim command is very helpful. We can hide this kind of merge operation as a background operation, and then we can improve the performance. This is one of good example. I mean, this is from the Microsoft. This chart show the more sustained performance by having the trim command, and also when you look at the industry, many new OS require the multi-core processor architecture. I mean, you are familiar with this kind of process migration paths. But today, single processor is not be enough. So everybody looking at the multi-core architecture, like a dual core, triple core. But this is mainly a multitasking. Is now mandatory. So multitasking need some low write latency in the timeout value for the uninterrupted audio video playback. For example, the processor and process speed doing the different way, different task. In that during the time, so in the processor B certainly need some write operation, but the processor A also need to some sort of read operation. At that time, the performance performance drop is occurred due to the internal write operation, as I mentioned, the merge operation. This is one of some critical area we need to improve the performance side. So in order to overcome that limitation, JEDEC defined the HPI command, the high high priority interrupt command. While the write operation is is done. So this is one of a good example. Those kinds of new command set and the feature is needed. Okay, with some different environment, and this chart to show the UFS. UFS is post eMMC the product. So the UFS define the different protocol, which is called the MPI. And they are defining the more higher speed, like a 300 megabyte per second bandwidth with a serial interface way. And also they are defining the NCQ and different mapping algorithm. That's the one of the reason the market driving the more speed from the flash storage device as well. So this chart to show the command queuing example. So I think, command queuing enhanced the performance because we can more efficiently handle the NAND flash issue with, more involving, like the command queuing, and we can reorder the command, and then we can operate different command set based on the NAND flash, status. Okay, so that will improve the system performance as well. And this is by having the more queue depths, we can improve the performance better, like write IOPS number and read IOPS number, and we can improve the better. Okay. So this is UFS standardization roadmap. Now we are discussing in JEDEC, and we're going to finalize spec 1.0 within this year, and then we're going to move to the next step. So we are discussing some new feature like NCQ and hybrid power, and due to that region, we got many new requirements from the system and this processor and end customer. So we are trying to accommodate new feature to meet their requirement. So conclusion, as I mentioned, the various NAND flash technology target the different market like SLC, MLC, and TLC with a different focus, architecture-wise and performance-wise. And so that's region, memory vendor, we have a more product lineup, but we need to make this kind of a different, taste for the different customer, usage. And also the high performance on the mobile system is now become more important. So that's region we are trying to improve our NAND flash, speed as well. We call toggle mode NAND. So we are having 133 megabps today, and we are trying to improve the performance up to the 400 megabps in the next generation. So those kinds of performance enhancement from the memory vendor, and also we are talking about some different approaches such as firmware, hardware approach and firmware approach to improve the performance and reliability. And also the NAND flash friendly system. Level solution is now become more important. So that's why we are trying to add more feature like a trim, HPI, reliable write on ECC, eMMC. Those are the very critical role in the managing high reliability and performance. And finally, command queuing architecture on the UFS. That's the one key movement to improve the higher performance. Especially the significant in the increasing the IOPS number, the random performance number. Okay, I finished my presentation, so I have 2 minutes left. If you have any question, let me try. Let me answer.
Hello. On slide number 9, I have a question. It's okay. Where you have the 3D NAND.
Can you say that?
Oh, slide number 9.
Slide number 9. Okay. Let me. Okay. I'm trying. Slide number 9. Which one?
Okay. And so I've been requested to say my name is Nat Collins.
Okay.
I'm currently unaffiliated. All right, that's slide 6. If you go forward 3, slide number 9, one before 10.
This one? 9. 2 more? That's it? This one? One more?
Forward. Yes.
Okay.
Okay. I'm trying to understand the 3D structure on the bottom left. It looks like the N plus would be shorting out that string of vertical control gates. What could you comment? I mean, what is the structure? Is it really N plus down the middle? And if so, what am I missing?
So if you're talking about the 3D, the architecture of a 3D NAND flash, you mean?
Yes.
So, frankly, it's really hard to say, talk about in detail about the 3D NAND flash in this meeting. So, If you have the question detail in the 3D NAND, please let me know. Let me answer the question through the email or some different way.
Okay, thank you.
Yeah, I mean 3D NAND is a little bit very some sensitive area. We are a little bit careful, so without NDI we cannot disclose the information.
Has it been published yet? Is there
It's not I mean we have some published information through the IEEE and etc. So as you know, we are talking about the terabit cell array transistor, which is called CAT. So if you refer those kinds of information, I think you can get some basic detail.
Thank you.
Okay.
Another question, Dan Lenoski from Cisco.
Okay.
Tony, you talked about all the different, specific flash directed towards different applications, right?
Yep.
With different wear and endurance characteristics. I'm wondering, is there any standard that actually retains on the flash memory itself the notion of its wear, or is it all placed on the controller's intelligence to know this?
So, the SLC is more or less. I mean, the TRC is more, please correct me if I'm wrong. Your question is the different technology, like say SLC, MLC, TRC.
I'm actually asking, it seems like you need a notion of an odometer on these things. How much before it's going to die? And I know in some sense it depends. Individual pieces die before others. But I'm not aware of any kind of industry standard or anything that sort of lets you know, hey, I've worn this much through. Is there such a thing, either on an SSD level that's defined kind of like smart data for rotating media, or something else that's stored on the flash itself that would, even as a consumer, would let me know that, hey, I'm using this flash in my camera, but it's pretty much worn out. I should get a new one.
Oh yeah, okay. So my understanding, the NAND flash endurance and some limitation it can be it's manageable. For example, SSD. So SSD, we have many intelligent feature which called a smart attribute. So the host side, they can easily recognize whether the NAND flash is almost wear out. So because by having some information from the storage side. So no matter we have a certain limitation of endurance level and reliability concern, but everything is manageable by having the hardware and software. But the question is how we can control those kinds of issues. Now is more difficult area is in order to manage the NAND flash better, the controller side need to understand more about the NAND flash basic characteristic. So how are we going to share those kinds of information? This is one of the area we need to discuss together. Like a processor vendor and the memory vendor, even OS vendor, we need to talk about the some level of maybe understanding, and also we need to share the some your expectation and our expectation and some challenge. Those kind of kind of discussion and collaboration will resolve those kinds of issues. Okay. Okay.
You'll be available for discussion and questions later on.
Okay. Yep. Okay.
Thank you very much.
Thank you.
Okay, thank you very much, Tony. Our next speaker is Ed Dollar. As I indicated, he's with Micron. He's actually the Vice President and Chief Memory Architect for Micron, and joined via the acquisition of Numonyx, where he was CTO of Numonyx throughout the history of the company. And prior to that, Ed was at Intel and at IBM, also in senior roles. So his talk, again, is going to be on non-volatile memory, sort of looking at the same things that Tony were looking at, the futures and challenges, and in particular phase change memory, how that factors into the puzzle as well. So Ed?
Where's the remote control? Here we go. Hi, good morning, everyone. Thanks for the introduction. My name is Ed Dollar. I thought what I would do here this morning is I've got about 45 minutes or so, and I think for the first 25 minutes I'll try to go through some foils as quickly as I can. And since this is a tutorial, what I actually think would be better was to take some Q&A. And Sean Eilert, one of our senior principal engineers, is with me, and I thought maybe for the last 15 minutes I'd bring him out and the two of us can go through questions that I don't cover in the information. There's the typical legal disclaimer. You know, what's interesting about my role is I generally spend most of my time about 3 to 5 years from now thinking about technologies and applications of those technologies and where I see things going. And I think what you heard from the earlier presenter about the history of NAND, where NAND is, and some of the roadblocks that we see these fundamental technologies blocking into. NOR technology is something that is near and dear to my heart, but frankly speaking, NOR from a technology standpoint and frankly from a market standpoint is kind of flattening out. We don't see NOR scaling too much beyond 45 nanometer. NAND, our company today, is producing 25 nanometer. We just announced a TLC 25 nanometer product actually last week, and so we're continuing to move that technology along. PCM today, we are selling on 90 nanometer. We're selling it to guys that are seeing ways to take a technology that's quite a bit different than the others, as I'll show you, and try to use them in applications that garner the value that the technology has to offer. And so NOR scaling, I think I mentioned, you know, 45 nano, maybe 32 nanometer. The fundamental cell is limited by channel hot electron injection. We just can't make that channel any smaller. And so, as I said, we're clearly on a path to 45 nanometer and always looking to see if we can make it smaller. NAND, I think you heard enough about NAND. Clearly, electrons are the issue. I think our 25 nanometer technology, we're probably talking about 50 or so electrons that separate our states, about 100 millivolts or so between the states. And so fundamentally what you're seeing is the technology itself as we scale it, looking different every time we scale it. I was at the Flash Memory Summit this week, and I challenged the audience to give me an analogy for anything ever that every time you come out with a new product, it's worse than the old product. And that's fundamentally where we are with NAND technology. And so the question is, well, what do we do as an industry to deal with that? And so my fundamental opinion is this decade, somewhere around the middle of this decade, we're going to hit into a technology wall. And it's going to be on any technology that uses charge storage as a basis. We're getting to the point where it's just fundamentally difficult to deal as we scale these technologies. And so what I want to talk about today primarily is something that our company is investing in. Certainly our competitors are investing in this. And that's phase change memory. It's certainly moving away from electrostatic storage to something completely different. Phase change memory, again, I'm assuming there's multiple degrees of understanding of the technology sitting here in the room. Phase change memory is a heat-sensitive material where we use heat to change the crystalline structure from an amorphous to crystalline, and we detect the current change in that. It's the same technology that was used in rewritable CDs, where instead of using a laser, we use a localized resistive element to heat the technology and to fundamentally just change the resistance. So in rewritable CDs, you take the reflectivity of the material into account. We take the change in resistivity, and that gives us the separation that we can measure states in. And so at a very high level, what this chart shows is fundamentally how phase change memory, again, very qualitatively, compares to DRAM and to NAND. Every time we walk into a customer and we want to talk about PCM, it doesn't take more than a minute or two before they want to talk about the cost of the technology. And I think I've got a separate slide on that I'll go into. But fundamentally, PCM is very comparable, actually a little bit cheaper fundamentally than DRAM. NAND, clearly from a cost standpoint, theoretically is probably about 20 to 30% lower cost from an SLC standpoint on a given node. Write latency, DRAM clearly the highest, NAND clearly the lowest. PCM kind of puts itself in the middle there. Write endurance, of course, DRAM very, very good, theoretically infinite. NAND endurance is on the bottom comparatively, and as you've heard and as I'll show you, certainly getting worse. Read latency, PCM is more DRAM-like, talking about access times in the sub 100 nanoseconds relative to NAND in the tens of thousands of nanoseconds. PCM also has a DRAM-like attribute that's bit alterable. So for those that are used to dealing with erasure in a phase change memory product, if it's well architected, erasure is not in the foreground. There is no erasure, you just bit alter the device. And of course, fundamentally, the difference between PCM and a DRAM is it's non-volatile. And so I won't go through these in great detail, but I will. It's included in the material, and if we want to go through Q&A, we'll go through this. A couple of things I do want to point out. Write latency on PCM, if you look at it compared to NAND, theoretically we think we can get about a microsecond write latency as compared to NAND, which is in the 500 microseconds. Read latency, again, PCM, very DRAM-like. Endurance, I'm being gracious by saying NAND is 10 to the 5th, maybe going to the 10 to the 4th. We fundamentally believe and have demonstrated that with phase change memory, clearly 10 to the 6th and 10 to the 7th are things we fundamentally believe we can achieve. So theoretical cost, the reason I say theoretical cost, I think it's important to start with theoretical. The reason theoretical is not truly applicable is because today we are shipping PCM on 90 nanometer and NAND on 25 nanometer. And so the reason you have to look theoretically is you have to understand that NAND will slow down scaling, and our job for PCM is to move as quickly as we can to catch that and ultimately surpass it. So theoretically speaking, if you look at PCM from a single level cell standpoint, the feature size about 5.5 F squared. DRAM's about 6, NAND is about 5, somewhere in that neighborhood. So we fundamentally believe theoretically the cost of PCM is about 20% or so more than NAND if I could magically align the two today and put them both on 25 nanometer. So it just gives you a frame of reference from a theoretical standpoint. Obviously the challenge we have as an industry today is theory doesn't matter when you walk into a customer. Of course it does. They want to understand the scalability of the technology, where it's going, et cetera. But the reality is we're generations behind on a new technology. And so bit alterability, here's kind of a marketing slide. I apologize for that, but it's a pretty good analogy for what bit alterability means. Now for a hardware guy, bit alterability is I don't care. I'll let the software guys handle bit alterability, but you can usually tell who the software people are when you want to talk about the value of having a bit alterable non-volatile memory. And so fundamentally what you're seeing here is the difference between if I wanted to change a single bit in a NAND device because somebody calls and says my new phone number changed by 1 bit, what you have to do to a NAND device to change a single bit, that sequence of commands, versus PCM is you fundamentally just go in and rewrite that bit. So the amount of simplicity that comes along with a bit alterable device is what is trying to be portrayed here. And so endurance and retention, you know, this is something that I probably spend an enormous amount of my time on with customers, is first and foremost trying to understand what the usage models are in their application. And I think the gentleman that spoke before me did a great job of talking about these fundamental usage differences. Down here, these guys can use 3-bit per cell. These guys can use 2-bit per cell. These guys, 1-bit per cell. And even then, I'd argue things are going to start to get hard. What you're seeing here is that different applications require different usage conditions. And what I find very interesting about this market, if you look at the NAND market, for the past 10 years, that market has been driven primarily by usage conditions that are extremely low. In other words, if I go back 10 years and look at 90 nanometer NAND and we were talking about 200,000 and 300,000 endurance cycles, the reality is that most customers of the technology in those applications were 10, 15, 20, 30 cycle requirements. But what's interesting about that is that market drove this 18-month cadence of lowering the cost of NAND memory. And so that's a beautiful thing, but what that's created is this market now where we have this extremely low-cost memory technology where guys are coming out of the woodwork saying it's lower than DRAM, and how do I use this technology? And there's a gap between the other way in technology capability and what the applications are. SSDs in the enterprise are a phenomenal example of what I'm talking about there. And so what we have to do over time is figure out how to use the technology to the best we can by managing that technology. But fundamentally, what I believe is some of these new technologies, like PCM, even if they're not on cost parity, because of the cost at a solution level, will absolutely be making headway faster than probably most think. And so this is a graph that tries to portray this. So what you're seeing here is, let's just assume for a second that PCM delivers 1 million cycles. I can tell you for sure that the PCM that we have and we cycle, we easily get 1 million cycles. I'm being very gracious, I think, for NAND. Assuming SLC, there's enterprise level NAND that our company produces where we get hundreds of thousands of cycles. But clearly that is absolutely something that's going to be difficult to maintain as we scale the technology. And so if I look at data retention as an example, this is kind of an interesting chart. I've been involved with the IEEE floating gate standard. You saw the chart that presented earlier about how data retention requirements now are basically, instead of it being 100,000 cycles and 10-year data retention, it's whatever your endurance spec is, it's 1 year after that. So if I'm putting out a 3-bit per cell product and it's a 100-cycle part, then data retention is 1 year after 100 cycles. And so the interesting thing about PCM is that what we have found is that data retention is not a function of endurance. It's always been a function of endurance for any floating gate technology, whether it's NOR or NAND. It's just that 10 years ago, that gap was so big that we always said, hey, 100,000 cycles and 10-year data retention. Now we're at the point where if it's 100,000 cycles, if you can get a 1-year data retention, you're probably doing pretty good. And so if I look at one of the fastest growing segments, SSD is clearly going to drive the volume for the non-volatile memory industry for the next several years. And so the real question is, what do we fundamentally think that's going to look like? And so what's interesting to me is that if I pause a second and say, well, what do I see going on in this industry? As I said, SSDs are, in my opinion, at the infancy of what I think the market could potentially do. And so fundamentally what that means for us as NAND suppliers and memory suppliers and the whole ecosystem around SSDs is there's a tremendous amount of work that has to happen to develop that TAM. And it's going to be around the management of the memory technology and ways that we can architect solutions based off of what customers are going to do with those products. But what I want to show here is that as we start to see SSDs making their way into what I would say historical interfaces, SATA interfaces as an example. What we're clearly starting to do, and this is what I love about this business, we used to debate for many years, are SSDs really going to happen? And to me, I just spent a week down in Santa Clara where there was no doubt in anybody's mind sitting at that Flash Memory Summit whether or not SSDs were going to happen. It was more about how, and how do we remove bottlenecks to really increase the benefit of putting SSDs into these computing platforms. And so fundamentally as an industry, it's going to ramp, the whole hockey stick ramp. I mean, I absolutely think that's going to happen. But additionally, what's going to happen is you're going to start to see interfaces start to get adopted for these solid-state solutions. In other words, taking an SSD off of a SATA interface, putting it on a PCIe interface, for example, allows you to move traffic much, much faster. And my guess, by the way, is that there's other things in the work, there certainly are at Micron, where we think there's even better ways to take advantage of solid-state memory technologies such that we can move information in and out of them faster. So what's my point? My point here is that the minute you start to think about moving to faster interfaces, guess what happens? You start to move more information in and out of these solid-state memory devices. And so here's a, don't get hung up on the exact science of the numbers that I'm going to show you here. I did these numbers in a spreadsheet just to kind of make a couple of points here. And so what I want to show you here for a second is let's assume that I take a PCIe interface, and I think many of you know that there's companies out there today that are building SSDs sitting on a PCIe interface. But the minute you go to a PCIe 2 interface in a BI-8 mode where you're talking about very high speeds, 4 gigabytes per second, if I assume for a second that 100% duty cycle, and I'm only writing 10% of the time, the amount of information that you're going to move over that bus onto that NAND storage device is about 34 terabytes of information per day. So when you go talk to guys that are doing high performance computing, high frequency trading, guys that really beat on these SSDs, these types of applications become a reality. And so the real question is, well, let me just, if you assume that the data I showed you around endurance on that other slide was a reasonable proxy for endurance, and I assume that I'm sitting on a PCIe 2 interface, let's assume for a second that I've got a platform that's got multiple cores, and I want to put a bunch of 64 gigabyte SSDs on those cores for localized temporal data. Then what we're fundamentally saying here is that the amount of NAND, given those endurance charts that I showed you a couple of slides ago, that you would need just to keep up with the endurance at a 64 gigabyte drive starts to go up dramatically. And so my point here is that things are going to get faster. There's no doubt in my mind. Every customer that I go talk to says, I love NAND, but I got bottlenecks in my system that I need you to help me get out of. First of them, obviously, is the interface, and of course, there's always software bottlenecks that have to be optimized to take full advantage of a low latency, high speed I/O device. And so what this shows is, under that condition, the amount of PCM required is 64 gigabytes. Why? Because those million cycles seem reasonable. Now, one argument against what I'm telling you is, well, hang on a second. If I'm going to be building terabyte drives, then I should be able to amortize that cycling over a terabyte, and then maybe I'll need less memory to do that. And the answer to that is, yeah, you're right, you can do that. The point that I'm trying to make here is that for a system that requires, in this example, 64 gigabytes of non-volatile storage, the system level cost is what fundamentally matters. And we've got a lot of customers that, as much as they might like a terabyte of NAND storage, 64 gigabytes to 128 gigabytes per core is something that fundamentally we think seems like a reasonable density to get an optimized computing platform that can utilize a very low latency technology. So let me talk about latency. And so, this is a graph that I've used for a long time. It's important to understand when we talk about the difference between bandwidth and the difference between latency, right? Bandwidth, everybody knows bandwidth is generally something that's fairly easy to fix. I use a highway as an example. The way you get more bandwidth on a highway is you put more lanes on a highway, right? But latency is very different than that. Latency means, I have to add something faster. So I'm obviously showing a Prius versus, I think that might be a 430 Ferrari. It's fundamentally, you need something faster to get that latency. And so, what I fundamentally believe is that if you look at the way memory hierarchy exists today in the computing world, you know, the way you get bandwidth improvement, if you just put more things in parallel, right? This is why, you know, Google server farms give you as much memory as you want for your inbox, is because they have tremendous amount of storage sitting there in parallel. Latency, you're either going to add more DRAM to your system or you're going to add something faster from a non-volatile memory standpoint. Of course, as we all know, those are SSDs. And so what you know, it's funny, you look at that chart and it's like, well, yeah, it makes sense. We've got tape that's a seconds, we have disk that's milliseconds, we have DRAM that's nanoseconds. Something microseconds slipping in the middle there seems pretty fundamental, okay? And so the real thing going forward is if I look at PCM from a latency standpoint, and let me assume for a second that random latency is a day for PCM. I'm just using this to normalize the latency of PCM relative to these other technologies. So PCM, if PCM is a day, then the latency of an SSD is 17 days. For a hard disk drive, compared to PCM being 1 day, you're talking about 9 years. I'm trying to give you some sort of proportional reference. Now, storage class memory is something where now I'm trying to pull out the interface speeds out of the equation, meaning I can get to that memory, storage class memory, and I think there's a gentleman from IBM that you'll hear plenty about a couple of presentations from now. And so storage class memory basically means it's not I/O, it's memory map, and I can take full advantage of a non-volatile memory that has sub-100 nanoseconds latency. Now you're talking 30 minutes relative to a day. So I wanted to try to normalize this just to give you a sense of something that most people can wrap their brain around. Instead of nanoseconds and picoseconds and milliseconds, days, everybody understands what a day is. And so storage class PCM can perform 800 database searches in the time it takes an SSD to do one. And so this is the magnitude of what we're going to see over time. And so this is something that I love because, you know, there's always questions. What's the value of latency in a computing platform? And so here's a couple of quotes that I've used that I thought do a really good job of summing it up. You know, Amazon, every 100 milliseconds of latency costs them 1% in sales. Google, an extra 500 milliseconds in a search page generation time drops traffic by 20%. And, you know, a broker could lose $4 million per millisecond if their electronic trading platform is 5 milliseconds behind the competition. So there's absolutely people out there that understand the value of latency. And so what I fundamentally think will happen as we advance this technology, as we get it closer to cost of DRAM, by the way, my rule of thumb is you need to be about 2x DRAM to be in this type of computing hierarchy. And we fundamentally believe we can achieve that, certainly by the middle of this decade. Once you get there, then what you're talking about is adding a pool of non-volatile memory that can look like main memory, can look like I/O if you want, but the true value of that technology is sitting as main memory. And so this is a slide I love because it says high-frequency trader, trading a mere milliseconds is like so last century. So if anybody's ever paid attention to what goes on in Wall Street, high-frequency trading, you know, I love talking to these guys because, A, they don't care what they're paying for the memory. If you can show them a solution that improves latency, you know, you've got them. And fundamentally, we've got the memory technology that we think can do that. And so at the end of the day, PCM, I think the value proposition of this technology, I think bit alterable just makes it extremely simple to use. Latency, you know, near instant access, DRAM-like access, where you're talking about, again, sub-100 nanosecond access. Endurance, I'd argue that our knowledge of endurance is still fairly small. I mean, we've only had one node of PCM technology for us to fundamentally collect data. You know, we've had tens of generations of data on NAND and on NOR, any of the floating gate memory technologies, that we really understand that. And for me, to have this level of goodness in this stage of the fundamental technology at 1 million cycles certainly gives me a tremendous hope for getting well above 1 million cycles. And then, of course, retention. This is kind of a double-edged sword. I'd argue that retention and endurance obviously go hand in hand. And what I mean by that is, if you're writing a lot, do you really need a lot of data retention? And so, there are certainly customers that will tell you they need it. I'd argue some of them don't. Are a couple of strange applications that I've run into over the years where certainly that happens. Where, yeah, they write it a lot, and then they don't write for a long time. And so those applications, I think, can fundamentally benefit. And so with that, hopefully Sean Eilert's close at hand. Here he is. And so as I promised, I wanted to save the last 15 minutes or so for Q&A. So please, if you have any questions, have at it.
I'm Sanjeev from Oracle. So what do you say about the power about this device as compared to DRAM as well as for NAND in terms of active as well as an idle? Where does it stand with these two technologies?
You want to answer that? Power?
Yeah, sure. So at the cell level, the power for PCM is clearly higher. In fact, it takes almost no power to do a write on NAND. But when you look at the product-to-product comparison, and you look at the write energy to PCM, because PCM's a lot faster. For writes, they're about equivalent, and for reads, I think PCM's quite a lot better.
And one of the things to add to that is we spend a lot of time optimizing our silicon around that power envelope. For example, one of the first products that we have on PCM is targeted towards the mobile market. And so what we'll do is we will manage how much we fundamentally do in parallel to manage the power at the cell level. And so as we, or not the cell level, at the granularity level, I should say. But over time, as we talk to customers, there's clearly customers who care about power, and then there's guys who are willing to put jumper cables on the part if you can give them extremely low latency write. And we have to balance that based off of the application. Yes?
On your slide number 7, you show that phase change memory is made by taking a germanium, antimony, tellurium chalcogenide and changing it from a amorphous state to a single crystal state, or vice versa, in which case the resistivity or resistance changes from high to low. I'd appreciate, as a physicist, your explaining how you get a crystalline change in your device and are able to regrow from one phase to the other time and time again.
Sorry.
You want to take
Yeah,
that?
sure. Where is the speaker?
Right here.
Right here.
Okay. All right. So what we're doing, you can see in the diagram here at the lower left, the lower right, we have a heater element that is heating up as a function of the amount of current through Joule heating that is heating up that little bubble of material on the top. And so what we do is the diagram in the lower right there shows you that we take it to, by controlling the current, we take it to a crystallization temperature where if you leave it there for long enough, which frankly speaking is not very long, it will crystallize. In the case of the reset cell, when we're trying to get it into the amorphous state, we heat it up to the melt temperature, allow it to melt, and then freeze it very quickly by dropping the current instantaneously, or as close to instantaneously as we can. What we actually do is we sweep through a range for the crystallization, but effectively it's the same thing. Well, okay, so this is, I got to be a little bit careful here because at the product level, there are a lot of things that affect the write speed that are slowing voltages and so on. At the cell level, the reset operation is maybe 10 nanoseconds, a few tens of nanoseconds, and the set operations are 100-ish nanoseconds. But at the product level, looking forward, we think we can get the product level write specs for both sat and reset down to kind of the microsecond range, as I think that was in one of the foils that was kind of skipped over here.
Yeah, next question.
Hi. You talked a little about, you expected that the price would converge about 20% more than NAND, but where is it at today? And if I wanted to get my boss to buy it, how much would I?
That's a great question. I'm not sure I know exactly. I mean, just to put things in perspective, our 90 nanometer technology, when we first developed that lithography node, it was very much targeted as a NOR replacement, right? I mean, it's more NOR-like on our first product than it is NAND-like. That doesn't mean it can't be. It was just the way it was fundamentally architected. And because of that, it's a 128 megabit, very, very low density device in the grand scheme of memory technologies. And I don't even know what that fundamentally sells for. I would guess it's a couple of dollars. So, 8 times that, 8 times a couple of dollars is about $16 a gigabyte. And in the grand scheme of gigabytes, that's expensive. What we decided to do as part of our company to accelerate the cost curve is to skip 65 nanometer and go right to 45 nanometer. So we're on 45 nanometer from a technology development standpoint right now. We expect to be in production next year on a 1 gigabit device, so 8 times the density of our 90 nanometer node, and we will be sampling that 1 gigabit device this year. So we know there's a gap. Our goal is to try to move that gap. And by the way, we sell NAND, we sell DRAM. So the good news is we've got all the technologies, but we're trying to accelerate the PCM one as quickly as possible.
Ed, this is Aurangzeb, Sirius Consulting. I had a question, and you touched on it just a moment ago. How do you foresee density growth in this technology? Give me some feel for, gigabit is a big step. We heard that, and you're saying it'll get productized.
Yeah, so our product portfolio on 45 nanometer, we've got a 4 gigabit product on our roadmap for 45. When we go to the next litho, my guess is we'll start seeing 8 and 16 gigabit devices. So that should be probably around the 2013 timeframe.
Eric Seldar from Oracle, and I was also going to ask the density question, but maybe you could also compare it to the other technologies out there for storage from DRAM to hard disk.
Yeah, I mean, the beautiful thing about NAND is NAND today, we're shipping 64 gigabit chips today on 25 nanometer technology. So from a density standpoint, there's clearly a lot of room to catch up. Now, one thing to note, though, is this technology, we generally target for applications that value latency, and the majority of those applications that value latency, if you forget I/O for a second, are typically embedded applications. And for those applications, it's generally smaller density, and fundamentally that means it's generally smaller die size. So for example, for PCM, we're probably in the 50, 60 millimeter square die size. NAND, we're probably in the 125 to 140 millimeter square die size. Now that doesn't mean we can't take PCM technology and start building 135 millimeter square die. It's just going to be a function of our customers willing to pay for that technology. And that's the kind of mode we're in right now, is to try to figure out where that value is. We understand the value proposition, but fundamentally, as we build out our roadmap, build out our lithography curves, having those discussions with customers is obviously pretty important. Yes?
A couple questions. You mentioned the 50 electrons for 100 millivolt separation. If you do a quick calculation of that, the capacitance turns out to be something like 0.08 femtofarads. That sounds a little bit too small for me for the gate cap. Can you explain that? Second question is the slide that you have on top. If I look at the numbers there, is this a per cell current versus voltage? If that's the case,
which curve are you look? This
one right there. So that computes to around, for a write, around 7 watts. Second question about on the same slide is what is your time scale there? What's the separation between the crystalline and amorphous time? Third question on that one.
Okay, wait.
I forgot the first two already.
Okay.
Let me take a couple of your questions there. I remember the electrons question. So what was shown was the separation in states, the number of electrons from one state to another.
Yeah.
And actually, I think that data was for an MLC, a 2-bit per cell NAND device. And so you're looking at a few hundred millivolt separation in states. For when you move to 3-bit per cell, that separation gets cut in half.
Yeah, we're not talking about the charge as much as it is the separation between the states.
Yeah, but you mentioned something like 50 electrons, and if you make the computation for that separation, that corresponds to a pretty small capacitance, and that
it is a very small.
It is a very small.
That's right.
Comparable to a gate cap, 100 times. That's what I compute.
It should be very comparable to a gate cap. It's a gate.
No, it's 100 times less than a gate cap. That's what I'm saying.
Yeah. We can take it offline, okay. But these, in fact, the same graph basically was presented in the earlier presentation.
Okay. So can you comment about the 7 watts?
Yeah. So the powers here, we should have taken the currents off of the y-axis. That's not even for the 90 nanometer technology that we're producing today. The characteristic is the same. But the current goes, that's one of the nice things about the technology is as you scale the technology down, the power requirements to make the technology work also go down. And so this is for probably more than 100, well over 100, maybe 180 nanometer technology. And so you can roughly scale that with the lithography. Your third question was on the time scale, and I said before it's about a 10x difference. We try to keep a 10x difference between the set and the reset operations so that we can control them.
So do you provide thermal isolation between your cells, and what's the space for this thermal isolation? Is this just normal locos or what?
Isolation
thermal isolation between cells.
Yeah, this is an interesting thing. Today in the technology, proximity disturb is not a major factor. In fact, it's not a factor for us. And sort of by design, we design around any proximity disturbs through the cell design and through the algorithms that we use to control them. As we move forward, we've got the one thing working for us that the power scales down, but the cells are also getting close together. And so that's something that we're going to have to continue to watch over time. But today, the active cell is so very small compared to the distance between cells that that's not an issue.
And what sets your write endurance? Why you're not indefinite write endurance?
So we get into, I think we're running a little bit short on time. I want to get into some of the other questions, but there are a few failure modes related to frequent heating and cooling of the chalcogenide material. And the fact that you have it at a very high temperature, things tend to move around, and so you form different alloys.
Okay, thank you.
Yes?
Yeah, I have a couple of questions. One is that when you go from 90 nanometer to 45 nanometer, how is the usage model will change? Will it really, I mean, from an address space perspective, will it really make it discontiguous? Or, I mean, from a perspective of the endurance of the device, bad blocks are scattered around the device, and that makes the usage non-uniform. And the second question is that when you, what do you comment about the ECC protection on these devices in terms of compared to NAND or in fact for the DRAMs?
So I'll take the second question first. So because these devices that we're shipping are going for code storage, ECC is something that can't be part of that scheme. It's got to be a device that hooks up to a processor and reads like a NOR device and like a RAM device. So if there's any management going on, it's got to be transparent to the user. Your first question was around?
Yeah, the changes in reliability or endurance generation to generation?
No, in fact, you are jumping quite a bit from 90 nanometer to 45 nanometer. I believe for the last answer you gave, that is to increase the density and all that.
Yes.
So what is the effect of that on the reliability aspect in terms of bad blocks when it comes around?
Yeah, so just kind of reiterate what Ed just said. Generally, our products are aligned towards code storage. So from the user standpoint, there is no such thing as a bad block. There is no such thing as a bad bit. If there is, it's a reliability failure. And so we're gonna hold our 45 nanometer technology to the same, in fact, higher standards than we held the 90 nanometer. But on that point, when we start to put these into storage subsystems where error management is something that can work just fine, there's a possibility for enhancing the performance, getting longer endurance, et cetera, out of the device.
Yeah, just, you know, I think we're getting the hook here, but just let me make one more comment there and we'll go here. When we talk about 1 million cycles, it's a very different benchmark than, I would say, NAND at 1 million cycles. Because of the fact that the applications that are code sensitive, when we may say 1 million cycles, it's got to be a very high reliability standard. And so that's why I feel extremely comfortable about taking the techniques that the industry has developed over the past 10 years of managing a lossy media such as NAND. You apply those same mechanisms to a phase change memory device and you can increase that endurance a couple of orders of magnitude. Okay, we're done. We're getting the hook. Thank you, Vern. Oh, okay, go ahead. Great. Yes.
I have one more. Can you give us some idea about when you go from 90 to 45 nanometer, what is the read and write power scaling would look like as compared, take a reference of 90 nanometer as a reference and going to 45 nanometer, what do you expect in the write power scaling and the read power scaling for going for that?
Okay, so so we have two products that we're aligning to our 45 nanometer node. One of them is really targeted at wireless and embedded applications, in which case we scale the power down to fit within the envelope that's available to us, you know, maybe about 100 milliwatts kind of power. The other line of products that we're entertaining for our 45 nanometer node is much more aligned to compute applications where you know, power is important, but you're plugged into a wall and you have the power available. And there we're targeting something around a watt in the product spec, but that part can also write at about 300 megabytes per second. So we'll scale up to fit within the best bandwidth power window that we can.
I mean, if you're familiar with NOR flash, it's very similar. You know, most of the NOR flash that we sold was targeted for the wireless segment. And even though NOR fundamentally writes faster than NAND, it's an extremely power-sensitive issue that we have to manage. So we do less in parallel because NAND at a cell level uses Fowler-Nordheim tunneling. The current is very low and there's very efficient programming. And so you can do much more in parallel. NOR, it's a very inefficient programming mechanism and it's a high current operation. And so we have to play with that like we do with PCM to try to wrap the application requirements around that power envelope.
Yeah, I was just looking at the maximum bandwidth supported at that level. What would be the scaling? Suppose if I'm supporting X megabytes or X gigabytes per second for this device, what would it scale when we go from 90 nanometer to 45 nanometer for a read, for instance?
Yeah, I think the answer is what Sean said. I mean, you know, to achieve those requiremements, to get that really high bandwidth from a write standpoint, you know.
Yeah, the simple way to look at it is that you're going to get about for a technology node, you're going to get about a 2x reduction in the cell current, but there's a lot more to it than that, and even the interface power can be a dominant component.
Okay, next question.
Yeah, Ron Nicholson, unaffiliated. The basic technology, how amenable is it to have the NV integrated with random logic, and if so, what's the granularity of the basic technology if you integrate it with other random digital logic?
So it's very integratable. I mean, we clearly have discussions ongoing with companies that are looking at using our technology for integration, whether it's with a logic process, whether it's with another memory process. It's something that we think is clearly a fairly simplistic thing to do.
And if so, what's the granularity size? 1 bit, 1 megabit?
Well, that fundamentally just comes down to, you know, it's really dependent on how much die size you want to allot and then how many bits we can squeeze into it. I mean, that's really what it fundamentally comes down to. But no, I think, you know, from a technology standpoint, you can get in a, 8 millimeter square area, you can get, I'm trying to think off the top of my head. You can get a whole lot of memory, actually. You probably...
Yeah, you can get hundreds of megabits.
Yeah.
Yeah.
Okay, thank you.
Yep, last question.
Yeah. So, first question is that as you are behind the technology curve on lithography, you think you will be able to get closer to the general lithography scaling over time, like closer to 32 nanometer and 20 nanometer sooner than?
Yeah, I mean, it's, as I said, we're clearly in a situation where, bringing up any new memory technology, I was part of the original flash technology. It takes much longer than you think to happen. And so what we're doing in this time frame is because we're on 90 nanometer and because the technology fundamentally costs more relative to where we are, you better find somebody that's willing to pay you for that. Or option B is you continue to pour money into the R&D effort of the technology and you wait for these other technologies to crash into the wall. And so my opinion is there's a happy medium there. We fundamentally have people that are willing to pay for what they get for the technology, but we also know that the big segments that are being driven today are certainly going to take time to close that window. So, I mean, it's really not a simple answer.
And the last question is, do you see any fundamental issue that's going to impact your scaling, say 20 nanometer or 40 nanometer?
So we fundamentally believe that the PCM technology scales to the 5 nanometer standpoint. There's clearly going to be challenges over how we architect the array and some of the select transistors that are used to get to those memory elements. But from a fundamental technology standpoint, we see going down to 5 nanometers is something that's been demonstrated and achievable. Okay, thank you very much.
Thank you very much.
Thanks, Ed and Sean.